Okay, Boker Tov, good morning, everybody. People who can hear me, just raise your thumb so I can tell them. Okay, good. So let me remind you what we were discussing last time. We were discussing the Grassmann algebra, and there were some, I want to recall a few things. There were some things which were not correct in the previous lecture, so I want to describe that. So if I'm just reminding you, recall, the Grassmann algebra, Gn, is a direct sum of some spaces that we denoted by um, RNP. RNP is sometimes, it's the span of certain vectors E sigma, where the sigmas are these multi-indices. And so just in terms of notation that I forgot to introduce, some people refer to this space RNP as the pth exterior power of Rn. So this is kind of a common notation that you'll see. So these are vector spaces, and I want to correct something that I said. So the last week's proof, I gave a proof um, that whenever you have two vectors in this exterior algebra, in this Grassmann algebra, the norm of the wedge is bounded above by the product of the norms. And this is, I'm not telling you whether this is true or false. I put it on the exercise sheet for you to think about. But this is, the proof that I gave was wrong. And so in the notes, you're going to find a corrected proof in the case that U and V are so-called decomposable. Decomposable means that they're obtained as wedges themselves. Okay, so the exterior algebra or the Grassmann algebra has several structures. One of them is this wedge mapping, and it's equipped with a norm. The norm is the one given by the inner product that makes these vectors orthonormal. And I gave something that I called a proof, but you caught me. There was a mistake in the proof. Someone in the audience found the mistake. And when I tried to correct it, I realized that it was more complicated than I thought. But this statement is true. If you take two vectors with a special form, they are wedges of vectors in Rn, then these such vectors are called decomposable. Then the inequality written over here is correct, and I put a proof in the notes. Okay, and I also added an exercise to understand what happens with this inequality in the general case. Another thing about these notes, we had a proposition at the end of the lecture. So let me write it down again. So recall from previous lecture, also at the end, um, well, first of all, we had the notion of a co-volume. So if L0 in L is a subgroup of rank R, which means it's the span over Z of R linearly independent vectors, then the co-volume of L0 is the norm of this element of the Grassmann algebra. That's the main computational tool that I presented, but now we can take it as a definition if we like. And then I defined the operation of taking a sum of subgroups. So L1 plus L2 is just the collection of sums, or equivalently, it's what you get by taking all elements of L1 and L2 and looking at the group generated by them over, or their span over Z. And then we had a proposition. So for any L1 and L2 primitive, the covolume of L1 plus L2 times the covolume of L1 intersect L2 is less than the covolume of L1 times the covolume of L2. So in the proof that I gave last week, I didn't have time to finish a claim in the proof. So if you look at the notes, at the lecture notes that are on the course webpage, you'll see a complete proof. I'll just write that down. So complete proof in the lecture notes, including proof of the claim that I didn't have time to give in the lecture. Okay, so that's all I wanted to do in terms of reminding you where we are. And we also had this, this expression alpha I of L is the inf of the covolume of L0, where L0 and L a primitive subgroup of rank R. Of rank I, sorry. And we're thinking about these alpha i's as being another measurement of the geometry of a lattice. So, and that's what I want to discuss today. So we've collected a bunch of, we've collected a bunch of geometric characteristics of lattices. I'm going to give it like an informal discussion explaining some problems with our measurements of geometry of a lattice. So this is a kind of an informal discussion, but I hope you'll understand it as motivation. And so, what are the geometrical quantities we had? We had these lambda i's. These were the successive minima. We had something which is in the notes I called kappa i's. These are the lengths of the basis given by the Korkin-Zolotarev process. So I gave a process for constructing a particular relatively economical basis of a lattice. This is called the Korkin-Zolotarev procedure. And let's call the lengths of the vectors that you get kappa I. And then we had these alpha i's, which I just introduced a second ago. And all of these were basically supposedly measuring the same ideas, and they're all more or less derivable from each other up to constants that depend on dimensions. And so lambda I, let's make a notation. Let's say A with these kinds of, A and B are functions of lattices, and this kind of equal sign means, or asymptotic sign means, there exists a constant C independent of L such that for all lattices L, sorry, L in Rn, independent of L, and let me just emphasize that it could depend on the dimension. This holds. Okay, A and B are two functions of lattices, and we say that they're roughly equivalent and denoted by these brackets if they're equivalent up to multiplicative constants that depend on the dimension and not necessarily specified. And then what we had is that lambda I is comparable to kappa I, and alpha I is comparable to lambda 1 up to lambda I. So the first statement, sorry, both of these statements, I guess, are in the exercise sheet. And I sort of sketched the proof of the second statement in low dimensions. You can prove it by some kind of an induction. And so all of these, sort of on a first approximation, all of these quantities, the lambda i's, the kappa i's, the alpha i's, they're all measuring the geometry of the lattice. And the idea here being is that you kind of naively think of a lattice as being generated by orthogonal vectors, and lambda 1 is the shortest of these vectors, lambda 2 is the next shortest, and so on. But actually, it's not at all true that lattices are necessarily generated by orthogonal vectors, and we want finer information. So I want to point out some problems with these geometrical quantities, and then we'll try to sort of address these problems. So the first problem is all of these are not always well defined. So sorry, so we have for lambda I, kappa I, alpha I, we have the minimizers. In other words, there's a vector vi, for example. If we're talking about lambda I, then there's a vector vi whose length is exactly lambda I. If we're talking about the kappa I, again, there's another vector maybe whose length is this kappa I. If we're talking about alpha I, there's a certain subgroup of rank I that realizes this covolume. And so there are these minimizers that achieve these numbers, and I want to discuss some problems with them. And so the first problem is that these minimizers, let me move this over.
Sorry.
Yeah.
Can I don't know, I don't remember what you called Kolchin-Solotarev procedure. Korkin.
Yeah. I'll just say it in words.
Yeah, that's sufficient. Just
yeah, you'd start with the shortest vector, and you choose
and then
and then so kappa 1 is the same as lambda 1. It's the length of the shortest vector. You choose the shortest vector. If there are ties, you choose one of those possible shortest vectors. Then you project the entire picture onto the ortho complement of that vector. You get a lattice in one dimension smaller. You choose the shortest vector in that lattice. And in the original lattice, there was some vector. There were many vectors differing by v1 that project onto the shortest vector in the quotient. You choose the shortest of those, and that's your v2. And then you project onto this orthogonal complement of the span of v1 and v2, and so on.
Okay. Thanks.
So problems with these geometry things. The minimizers, the first one is the minimizers are not well defined. So we can have ties. And I gave you an example, the Leach lattice and the E8 lattice in 8 dimensions. And we saw that there are many, many, many different vectors, all of them realizing the shortest vector. So we're not choosing if there are ties, we don't exactly say how to choose these minimizers. We don't have any particular choice. We can also have problems finding these minimizers. So for a generic lattice, you have many near ties, which means the shortest vector is one. Say we're in dimension, I don't know, 30. The shortest vector is one of maybe 10,000 vectors who are extremely close to each other in terms of their lengths, and it's very, very hard to figure out which is the shortest one. This is quite important when we get to applications in computer science. So there are many, many possibilities for near ties. When you have near ties, everything is very, very sensitive to changes. For example, if you change the norm, these concepts sort of change drastically, specifically the choice of the minimizers, and so on. Another problem that we saw is that the VIs associated with the Minkowski successive minima, so VIs realizing the lambda i's are not a basis for the lattice necessarily. We saw examples. The shortest vectors don't necessarily generate the entire lattice. They could generate a proper sublattice. Another problem is that the relation between these quantities is not so clear. So alpha I not necessarily realized by span over Z of V1 up to VI if the VI realize the Minkowski successive minima. So here, the alpha i's are chosen to minimize the co-volume. The VI's are chosen to attain the Minkowski successive minima. Naively, you might think that this is more or less the same, and so you sort of should have that the rank I subspace that realizes alpha I should just be the space generated by the shortest vectors, and that's just not the case. Okay, so all of these, I want to think about these as problems, and what I'm looking for now is some better idea of what the correct things to choose are. I want to have some canonical choices which don't suffer from these issues, and that's where we're heading next. So the solution to these kinds of problems is something called the Harder-Narasimhan filtration. So I will introduce it formally. That'll take a while. And then I'll go back to these problems and see like what we learned and what the moral is in terms of these problems. Okay, so we're going to do some examples before I introduce this explicitly. So these are examples that sort of illustrate this list of problems, so you get a better feeling. So let's define a lattice in 3 dimensions. So let's call it L0, and it's going to be the sum of 2 lattices, L1 and L1 is going to be a 2-dimensional lattice. And in the directions spanned by the x and y directions, the first 2 coordinate axes, and we're doing a direct sum with the vertical unit vector. And L1 is the hexagonal lattice rescaled to have covolume 1. What do I mean by that? The hexagonal lattice is the lattice generated by 2 vectors which are sides of an equilateral triangle. So when I mean by normalizing them, I want to choose them. This is the fundamental domain for this lattice is this parallelogram. And I want to choose the length of these 2 vectors so that the volume is 1. So this vector points in the unit in direction of the first standard basis vector. So I'll denote it by C times E1. C is the rescaling constant that I'm trying to find. In the orthogonal direction, the height here, this is a 60-degree angle, and so the height here is C times square root of 3 over 2. Square root of 3 over 2 is the sine of 60 degrees. Okay? And we're requiring that the covolume is 1, so that means that c squared times square root of 3 over 2 is 1. That's the area of this parallelogram, is the base times the height. So that means that c is the square root of 2 over the square root of 3. And you can do a computation, and you get something that's bigger than 1 by a little margin. So this lattice has its shortest vector of size slightly bigger than 1, and the covolume is 1. Okay, that's this lattice L1. And we're interested in the geometry of the lattice that you get by doing this direct sum decomposition. So let's figure out the Minkowski's successive minima and so on for this lattice. And so the shortest vector in the lattice, so every let me just write it down. Shortest non-zero vectors are plus minus E3. How do I know that? Well, it's a direct sum. So this direct sum means these two spaces are orthogonal to each other. Every lattice has a projection to this coordinate, and it has a projection to this coordinate. If the projection to this coordinate is non-zero, then we get some lattice in this hexagonal lattice, but the shortest vector in the hexagonal lattice is this length. And so the shortest vector shouldn't project to should project trivially down here, and therefore it should be in the space generated by E3. So these are the shortest vectors. So far, so good. So this is the shortest vector in this lattice. Let's compute alpha 2. So this is also alpha 1, as we know. Alpha 1 always coincides with lambda 1. Let's compute alpha 2. So let me remind you that if you have two vectors in 3 dimensions, u and v, then the norm, then their wedge is a 3-dimensional vector in what we call the Duplicor coordinates, and its coefficients are the determinants of minors of this 2 by 3, but 3 by 2 matrix. So you have u1 v2 minus u2 v1. This is u3 v1 minus u1 v3, and here you have u2 v3 minus u3 v2. This is possibly up to, yeah, I think I got the signs correct. So this is u wedge v, and so and this is an orthonormal basis, these coordinates. So the norm of u wedge v is bigger than the absolute value of one of these coordinates. And this is the projection. This is the this quantity here is exactly the determinant of these 4 numbers, which is the projection of this 2-dimensional lattice into L1. So this is either this was either greater than or equal to 1 if u1 v2 minus u2 v1 equals not equal to 0, or it's something else, which we're going to compute. So if this let me just write it in the following form. If the projection, if this quantity here is 0, that means that when we project these two vectors into this lattice L1, we get two vectors which are proportional. So what we get in that case would be, let me try it in this way, we're going to get K1 W plus L1 U3 wedge K2 W plus L2 U3 if this is 0 for W in L 0, L1, I guess I called it.
Sorry, can you go there again? You have somehow written there an absolute value, and then you make a distinction whether this is
I'm taking, okay,
zero or not.
alpha,
That's a bit weird.
alpha 2, let me explain. Alpha 2 is the minimal possible norm of such a vector, as long as it's non-zero, okay?
Mhm.
So the norm of the vector, obviously, since this is an orthonormal, these are coefficients with respect to an orthonormal basis, the norm is bigger than the value of one coefficient, which is this coefficient. This coefficient has a geometric meaning. It's these two vectors, u1, u2, 0, v1, v2, 0, they are the projections of the lattice to this two-dimensional lattice, okay? And now there are two cases. Either the projection is non-zero, or the projection is 0. If the projection is non-zero, that's this case. If the projection is non-zero, we have something that is at least the co-volume of this lattice, which is 1.
Mhm.
If the projection is 0, that means we can call the projection a multiple of W. That means that the projection is, the two projections are collinear. So there's a W in L1 such that the projection is some multiple of W. So the vector looks like this. The original U is W times something. That's a vector in the vector L, in the sublattice L1, and then some additional element in the E3 direction. And so this is just a rewriting of U and V, and I should have put a norm here. Norm symbol.
And in this case, it's
going to-
equality with the norm of U wedge V. That's all my confusion.
Oh,
So
yes. Thank you.
Okay. So you have, okay, I see.
Right. So maybe
Now that the norm is there, and okay.
So this should be here. And then here we have an, sorry. Okay, let's do this nicely. This should move here. And this should go inside. Okay? And these are the two cases. No, maybe I'll move this over. Okay?
Yeah, thanks.
Yeah. While we're at it, let's make it all nice and beautiful. Sorry. You get to watch me play with this iPad that I'm not used to. That's part of the deal. Okay, so I'm claiming that the minimal value, possible value, is achieved in this case, and you get the answer 1. And why is that? Well, let's analyze this quantity here. The second quantity, the vector that you see over here, this vector equals, so when you wedge things out, whenever W meets W, you get 0. Whenever E3 meets E3, you get 0. So what this is it's W wedge E3. I'm sorry, W wedge E3 multiplied by a coefficient. And the coefficient is this determinant. It's K1 L2 minus K2 L1. And this coefficient is an integer, a non-zero integer. If this were a 0 integer, we'd have the 0 vector. So this is, oops, non-zero integer. So this is at least the area generated by W wedge E3, which, since these vectors are orthogonal, this is W times E3, which is at least, which is equal to the norm of W because E3 has norm 1, which is bigger than the shortest vector in L1, whose length is 1.074. Okay, so what I'm getting is that in the first case here, I get at least 1, but 1 can be achieved if I take U and V to be the generators of L1. And in the second case, I get something strictly bigger than 1. So alpha 2 is, so alpha 2 is 1, and it's realized by the two-dimensional lattice L1. Okay, now I'm going to make a little graph of the heights. So let's make a graph. So graph the following numbers. K covolume L0, sorry, K log of covolume L0, where K is an integer between 0 and n, and L0 in L has rank K. So there's a little exercise with that I'm going to do. So let's do it for this particular. Maybe before doing that, I'm sorry, I wanted to emphasize something about this example. So let me move this a little bit. We're going to go there soon. So what are we seeing? We're seeing here that so lambda 1 is realized by E1, and alpha 2 is realized by the vector space L1, and E1 is not in L1. I said at the beginning of the lecture that we have this issue here. It's not at all true necessarily that the alpha i's are spanned by the shortest vectors. And we're seeing that in this simple example, right? The shortest vector is pointing in this direction. The smallest two-dimensional subspace is here. It's in this two-plane. Okay, so that was one of the points of showing you this example. Okay, let's now do what I wrote down. I'm going to take k's, which are dimensions, anywhere between 0 and n, and for each sub-lattice of that rank, I'm going to write down a point in the plane. Its x-coordinate is this integer k, and its height is the log of the covolume. So in this example, it's going to look like this. I'll do it over here. So this is for L0. Here we have the point 0, 0. Yeah, I'm going to do it in color. So this is the k axis, and there are 4 possibilities: 0, 1, 2, and 3. And we are going to put a point here because the covolume of the trivial vector space is by definition 1, and that log of 1 is 0. We're going to put a point here because the covolume of the lattice itself is 1, and that's the only primitive lattice in dimension 3. Now, what happens in, what's the shortest vector? The shortest vector has length 1, so it appears here. And then there are some more vectors in the lattice above this point. Okay, so this is the height of this one here is 0. That's the shortest one. The next shortest one is this number, which is log of 1.07. So it's slightly bigger. And then in 2 dimensions, again, you have the smallest covolume is again 1, and then you have other bigger covolume. So there's it's kind of an infinite picture that looks like this. So is the exercise clear? This is this axis the horizontal axis is this integer giving us the rank, and here we have the log of the covolume in that rank. Let's do the same exercise for another lattice, which is 1 minus epsilon times what I had before, L1, and 1 minus epsilon to the minus 2 times ZE3. So I'm taking the previous example. Previous example is this example here. I'm making the this direction, the two-dimensional direction, the hexagonal lattice, just a little bit smaller, multiplying it by 1 minus epsilon, and I'm making the orthogonal direction just a little bit bigger by doing this. So what the effect is going to be that with the same I'm still going to have these dots over here. And now the shortest vector in the lattice has been made just a little bit bigger. So it's up here. And the shortest one-dimensional subspace is just a little bit smaller, and it's down here. And let's do a similar picture for a third lattice, which is when we do the opposite operation. 1 plus epsilon L1 plus 1 over 1 plus epsilon squared Z3. Epsilon is some small positive number. So the effect that this has, it's making the two-dimensional lattice bigger at the expense of making the vertical direction a little bit smaller. So we get, oops, sorry, 0, 1, 2, 3. Okay, is the procedure clear? This is what I'm doing. I'm drawing a kind of a set in the plane, and the things that I care about are these quantities, which are these minimizers that we discussed before. I want to understand their geometry. And what are you seeing here? You're seeing that in the first example, there were these tides. All of these numbers were all 0. All these heights were 0. And when I make these perturbations, some of them go up and some of them go down. Let me just show you a picture of this. Yeah. Here's another picture that you see in some of the papers. This is a paper of Kesselman. And so he's taken some three-dimensional lattice, and he's drawn these points that I mentioned before. And in his example, both alpha 1 and alpha 2 were both smaller than 1. So when I took logs, I was underneath this horizontal line. And what you're seeing actually, which is interesting, is you're seeing these gaps here. There's nothing in here, there's nothing in here. And that's, you're going to see why in a moment. So this is a kind of a picture that shows up in an actual lattice. Okay, so, and we're going to be interested in this line at the bottom of the picture. Okay, so let's explain what the line is that we care about. So define, oops. The set of points that I just, let me denoted by, set of points that I just drew, I want to denoted by curly L. So that's the following thing, log covolume L0, such that L0 is in L, L0 has rank K. K goes from 0 to N. So this set curly A is the set that I just wrote down, and then I'm going to define another set A greater than or equal than, and that's the set of k comma y. It's a set in the plane k comma y, where again k is in the same range, and y is bigger than the inf of the numbers that we saw before. So I'll just write y is bigger than alpha k of n. So at the bottom of these pictures, this height is the log. I should have put in the log. This height here is the log of alpha 1. This height here is log of alpha 2. And I'm taking all the points ky where y is bigger than the log. So let me draw it in a new color here, just so you see this in this blue color. It's just this line here, this line here, this line here, this line here. So the blue is this set. Okay, and finally, the extreme points on the bottom of the convex hull of A form a polygonal line called the profile of L. So let's take a look. What are the extreme points? I'll draw some lines first. So, and then I'll go back to our examples. So we have these pictures that look like that, basically. Now we're taking the convex hull of this set. And so we're sort of filling in everything here. And in particular, we fill up. So it sort of looks like that. We're filling up things. And this picks out some vertices which are special. They form, the bottom boundary of this picture is a union of lines connecting those dots. And at these vertices, we actually have a bend. So it's really a graph of the slope passing from one line segment to the next. The slope strictly increases. And if that happens, this is called an extreme point. An extreme point of a convex set is just formally a point that can't be written as a convex combination of any other point. So except for this point here, and this point here, every other point in this picture can be obtained as a convex combination of other points. The exceptions are these 3 points. These are the extreme points. They form the profile. Let's go back and look at our examples. So the profile here is the lines connecting these 4 points. Say this point here would be the convex combination of, I don't know, two other points on both of its sides, and so on. In the example that I gave before, one more color, let's go to green. The profile in this example has 2 vertices. So in green, these are vertices of the profile. Every other red point is not an extreme point. So the profile is the horizontal line connecting these 2 green points, and every other point is not an extremal point. In this example, you see in particular that these 2 points are on the line, but they're not extreme points. In this example, it looks like that. And in this example, and these are the extreme points. And in this example, it looks like that. Okay? Is my procedure more or less clear? Okay, now I'll state a theorem. Um, so the minima alpha I realizing the heights of vertices of the profile are the form log co-volume of Li, and the Li are unique, i.e. cannot have Li prime in L different with the same co-volume realizing Fi. I said that in general, you can have ties for the shortest vector, ties for the smallest I-dimensional sublattice in terms of co-volume. But if you are a vertex of this profile, then the minimizer is unique. That's the first part of this statement. Second part of this statement, we have the subspaces, the sublattices, Li, in which rank Li co-volume, log co-volume Li is a vertex of the profile. Form a flag, i.e. they are nested. So it looks like this. The zero vector space is always there, and I'm going to denote it by L0. Then it contains it's contained in a chain of subspaces all the way up to L, and alpha I of co-volume so rank Li log co-volume Li are the vertices of the profile. So again, the point in this statement 2 is that these subspaces are nested. And this collection of subspaces, the collection of subspaces that I'll denote by star, is called the Heider-Sinhan filtration. And K is its length. So I'm inside the theorem, I'm sticking in a definition. It has some naturality properties, which I'll now describe. If I take any I between 1 and K and look at the filtration only taken up to the ith place, this is the Heider-Sinhan filtration of Li. And if pi from Rn to span of Li perp is the orthogonal projection, then the projections of these guys, so 0 equals pi of Li, pi of L1 plus Li plus 1, pi of L is the hydrogen infiltration of pi of L. I'll explain that with a picture in a second. And fourth property also involves a definition. If k equals 0, we say that L is stable. And for each I, Li plus 1 divided by Li, considered as a lattice in pi of span of pi of Li, Li plus 1 is stable. Okay, that's the statement of the theorem, which we're going to prove after the break. Let's take a few moments to digest this theorem. Let's just draw an example first. So now I'm sort of drawing a multi-dimensional example. So maybe this is 0, maybe this is n. At every subspace, you have some kind of numbers of covolumes. And I'm drawing I'm drawing all of them at first. And then let me skip ahead. And the ones which are extremal in the sense, in the sense that I explained, sorry, I'm going to write down in green. And so I get some kind of a collection that looks like that. And I connect the dots. And what I see is some special dimensions where we get extreme points. Okay, now what I'm telling you in the first item here, recall that in general, we could have ties for the successive minima. We could have two simultaneously shortest vectors that are not collinear, and similarly in every dimensions. But I'm telling you that in these dimensions that are vertices, we see unique vectors realizing the minima. So there's not a non-uniqueness problem in these special dimensions. In the other dimensions, there could be ties, but not in the special dimensions, which are vertices of this profile. Also, I said that we don't necessarily have to have nesting of the geometric minimizers in general, but item 2 says that we do have nesting, again, if we only look at what's happening in the dimensions of the profiles. These LIs are living in the dimensions which are the vertices of the profile. So in this case, there's the two trivial points in this. There are 2 points which are always in this profile, which is the this point and this point. And every other point gives us a non-trivial sublattice, which is unique in its dimension, and they're nested. That's property number 2, the nesting. Property number 3 says that if I care about this special lattice, say, and I want to understand its filtration, every lattice has a filtration. If I want to understand its filtration, all I need to do is look at this part of the profile that I already have. This particular point corresponds to a sublattice of the lattice realizing this height. And so this profile is actually the profile of this sublattice. And if I want to look at the projection of the original lattice modulo this lattice, I can also reconstruct the profile. Essentially, it's this piece of the picture. It's up to some renormalization that makes this higher you can figure out the geometry exactly, this gives us the picture for the profile of the quotient lattice. So if you are used to group theory notations, let me just write something in this form. You can think of this kind of short exact sequence where L0 is a subset of L, and L over L0 is a lattice that I obtained by projecting L onto the orthocomplement of L0. So that's kind of a, this is not the same notion of a short exact sequence exactly as you see in groups. It's, I want to sort of have a particular group in mind as my quotient, which is with a particular geometry. And what the axiom 3 is telling you is that if you know the profile, the filtration of this guy, and you know the filtration of this guy, you can combine them to form the filtration of this guy. So sort of somehow the filtration behaves naturally with respect to these short exact sequences. And the final item is that, so what's a stable lattice? A stable lattice is something that looks like this. This is 0, this is n, and there's a, oops, so you take, this is the profile. It's just a line like that, which means that all the other points are either on this line or above this line. So in some sense, what the last item is saying is that there's some special lattices called stable lattices. Those are the lattices for which the picture looks like this. And in the subquotients that you get by considering the projection of the lattice here, modular lattice here, what you always see is stable lattices. So in some cases, these stable lattices sort of form the basic building blocks of all lattices, and all lattices can be obtained from stable lattices by these kinds of operations. That's kind of like the philosophy of this theorem. Any questions about the statement?
Yeah, I have a question.
Yeah.
Where does the log come from? This seems like a magical thing.
The log will become, you'll see that the log will become helpful when we do the proof. If we were to work with the original co-volume here, without the log, then it would just have the effect of just pushing these points up in some way. So the vertical axis would be multiplicative instead of additive, and points would be further up. And this profile idea wouldn't be sort of the correct thing to look at. You'd have a more complicated expression, but it'll be just equivalent. So this is very convenient to take the logs, so that we want to define the extreme points. In order to find the extreme points, it's easiest to think about this as a convex set and think about the extreme points of a convex set. And if you do that with a log, you get the correct definition. That's all.
Okay, can I ask another question?
Sure.
So the extremal points will be the ones where there is a single minimizer, right?
Yeah,
and
that's part of the theorem.
That's what we're going to prove.
Right.
Okay. Thanks.
There could be unique minimizers in other dimensions, but all I'm saying is if you're at an extreme point, then minimizer is unique. Okay.
Okay, thank you.
This, I'll just say 2 more words about the history, and then we'll prove this after the break. So this filtration was studied by algebraic geometers by these names, Harder and Narasimhan, in the 70s, and was given a kind of this geometry. It was sort of defined more formally, and it was given this kind of geometric definition in terms of these this profile by someone named Daniel Grayson in the 80s, and this has not really been, you won't find this discussion usually in the standard literature on lattices. But in recent years, it's become clear that this object is very, very natural all of the items in this theorem, you can think of them as somehow resolving little problems or glitches with the Minkowski successive minima. So in some sense, they carry all the important information of the Minkowski successive minima, and they carry them in a natural way. They behave naturally with respect to certain operations. They are they give you a nested sequence. And the way to think about this, about these filtrations, about these flags, is the following. There are two cases. Case one is the stable case, which is this case over here. And in that case, what you should have in mind is that we don't have any particular information about short vectors or short I-dimensional subspaces for any I. And so in other words, the lattice is somehow kind of uniformly long as it could be. And then the way to think about it is all these Minkowski successive minima and all these other geometric information, they're not really very meaningful. They're not very robust. They change. There are a lot of ties. They're very delicate. And they shouldn't be thought of as being some kind of strong geometric, of having a strong geometric meaning attached to particular vectors or to particular minimizers. That's the first regime, is this stable regime. And then the general regime can be, the general picture can be obtained from the stable regime by a kind of taking these profiles in all these subquotients. All of these steps in the profile correspond to certain subquotients like this. They're all stable. And then we sort of build up our lattice geometrically, inductively in steps using this kind of, we have information about this, we have information about this, and we're trying to understand information about this. And all the things which appear in the filtration are meaningful. They do form a filtration, there's nesting. They do have unique minimizers. And this is kind of a very, very useful set of properties for these filtrations to have. And we're going to see some examples later in the course. Okay, so that's the sort of the motivation for this theorem and the statement. And now let's take 10 minutes and prove the theorem, unless there are any other questions.
I have a...
Yeah.
No, it's okay, Manuel. Go first.
I have a very vague question. This looks very much like the Newton polynomial. Is it in a... Or is this
sure.
just... Okay.
I'm not sure there's any, maybe there is. I'm not sure there's any obvious relationship.
Okay, and I have maybe, so the question is whether there's some kind of classification of these stable ones or something like that.
We're going to discuss that. So the vast majority, what will end up is that the vast majority of lattices are actually stable. Most lattices are actually stable in a very strong sense. And no, there's no classification, but often when you can, when you're faced with a certain problem about lattices, the strategy is to first solve it for the stable case. It's sort of like the simple case, maybe in group theory. You make a reduction to the stable case, you prove it for the stable case, and if you're able to do that, then this filtration lets you extend what you want to prove to all cases. That's sort of the way it appears in proofs. All right, let's take 10 minutes and continue. Okay, let me continue. So the proof is going to be very geometrical. And so can people hear me? Please make some kind of,
Yeah, we can hear you.
okay, good. So the proof is geometrical. It will be based on just a geometrical interpretation of the following inequality. We had the inequality covolume L1 intersect L2 times covolume L1 plus L2 is less than covolume of L1, covolume of L2. And if we take logs, then that transforms. This is responding to Shai's question. We take logs, that transforms these products into sums. And so we get that the log of the covolume of L1 intersect L2 plus the log of the covolume of L1 plus L2 is less than the log of the covolume of L1 plus the log of the covolume of L2. And I want to interpret this inequality and I'm going to give it the name, the parallelogram diagram. So let me draw 4 points in the plane. So suppose L1, L2 are subgroups of L of rank, let's say K and L. And I'm going to give names to the ranks of the intersection and the ranks of the, well, of the sum. So the rank of the sum, let me denote by M, and the rank of the intersection then becomes K plus L minus M. And let me just give these numbers more suggestive notation. So I'm going to call K x1, x because it's the x coordinate in the diagram that we're drawing, corresponding to L1. L is x2, N is x of the sum, and K plus L minus N is the x coordinate of the intersection. So those are my notations. And let's let, similarly, y1 be the log of the covolume of L1, and that's for I equals 1 and 2, and y plus the log of the covolume of L1 plus L2, and y intersect the log of the covolume of L1 intersect L2. And we can draw 4 points in the plane. Maybe this is x plus y, sorry, x1, y1. And what I want to claim, let me do this properly, is that I can, oops, I'm sorry. Let me complete this to a parallelogram. And so, why don't I'll move things a little bit so I have more space here. I'm going to complete this to a parallelogram by defining, let me write that over here. So y intersect bar to be the same formula that I had here. So this is y1 plus y2 minus y plus. And so this means that the vector x intersect y intersect bar is the vector x1 y1 plus the vector x2 y2 minus the vector x plus y plus. Or in other words, it means that these x's and y's, these vectors form the vertices of a parallelogram. So where does the next, sorry, now I confused myself. What are the parallel lines of this parallelogram? They are here. So this point here is x intersect y intersect bar. Okay, so far? And now, what is the inequality? The inequality is this inequality, which in our notation means that y intersect plus y plus is less than y1 plus y2, or in other words, this means that y intersect is less than or equal to y intersect bar. So the height of the actual point x intersect y intersect is smaller than the height of the extra vertex of the parallelogram. I drew 3 points corresponding to this data. From those 3 points, I completed them to a parallelogram. There's a unique way to complete them to a parallelogram, so that this is a diagonal and this is a diagonal. And the inequality that we had tells us that the true value of the height of this point is less than or equal to the height of the point on the parallelogram. That's the meaning of the inequality in geometric terms. Okay, let me scroll up and show you a diagram from Grayson's paper. This is Grayson's paper. You have the LIs, the points that you're seeing are the points that realize the some sublattices of a lattice L. And this is the parallelogram that I drew. And the height corresponding to the covolume of the intersection is always below this vertex of the parallelogram. And what does this mean for our, in case that these points, L1 and L2, and maybe this point as well, are extreme points of this picture? We get a contradiction, right? Because we get that the last point is somewhere where it's not allowed to be. If this line is an extreme, is connecting 2 extreme points of our diagram, then the entire diagram has to be above this vertical line. And so if this point is above it, this point is forced to be below it by the parallelogram rule, but that's not allowed. So this is the whole idea of the proof of the theorem. So now with this in mind, let's prove the theorem. So proof of theorem. Let's do statement A first. So suppose K log covolume alpha K is a vertex of the profile, and alpha K is, sorry, log alpha K. Alpha K is the covolume of L1 and the covolume of L2. So suppose we had a tie in the definition of alpha K by 2 subgroups of rank K. So that the minimizer is realized twice. Now we look at the this diagram. In the parallelogram diagram, we get that x1, y1 equals x2, y2. So the line connecting x intersect y intersect to x plus y plus is below this point, and this contradicts the fact that this point x1, y1 is an extreme point of the profile, unless this line, let's call this line L is a bad, I've used L too many times, so let's call this sigma. Unless sigma is degenerate, and what does it mean to be degenerate? A line, it's a line of length 0, which means that x intersect is x1 is x2, which means that the dimension of L1 intersect L2 is equal to the dimension of L1. Which means that that L1 equals to L2 equals the intersection. Okay? Is the proof clear?
I have an issue with drawing this parallelogram if x1, y1 is equal to x2, y2. What is?
I use the same formulas. It's just not, it's a degenerate parallelogram. So I'll draw it over here on the side. So here's a point, x1, y1, and it happens to equal x2,
Yeah.
2. And there's another point over here, and there's another point over here. That's it. This would be the midpoint in this case.
Ah, you lie on this line. That's resulting. That's the point. And then you're not extreme.
That means that, yeah.
Okay.
Yeah. You either lie on the line or you're actually this. So the actual point is either this point here or even below it. If it's below it, you're even above this line, but we're given that this line is a vertex in the profile, which means that it's strictly below. It can't be expressed as any convex combination of anything, of any numbers of this type. So we got a contradiction. Okay?
Yes, thanks.
B is very similar. Let's do B. So x1, y1, x2, y2 are both extreme points of the profile. And suppose that x1 is smaller than x2. So in other words, the rank of L1 is the smaller one of those two. So here's the first point, x1, y1. Here's the second point, x2, y2. And now we have 2 points, 2 additional points, and we're forming a parallelogram. It doesn't really matter how we form the parallelogram. But let me just, let me draw an imaginary line here. Consider this imaginary line, and there's a point corresponding to x plus y plus, and say it's above the line. If it's above the line, above the dotted line, then the other point, roughly here, this would be the point x intersect y intersect bar, this point here, And here we'd have the point x intersect y intersect. And so this, again, since this point is certainly below the bottom profile, we get a contradiction, again, unless everything is degenerated, in which case this point is here and this point is here. So this is the, I'm drawing the contradiction. So this is drawing the contradiction in case x plus y plus is above the line through x1, y1, x2, y2. If when in the, let me be fancy again with my iPad, if I'm going to copy this picture. All right, so now let's assume that this point is below the line, then we get a contradiction. Then we don't need then we don't need this point at all. This point is already below this line, and that's a contradiction to the notion of a profile. Again, the profile is the extreme points of the bottom of the picture. So anything, we can't have any points on this line or below this line. That's sort of the meaning of the extreme points of the picture. So we get a, in both cases, we get a contradiction, maybe. So maybe I'll put color around the contradiction. This is a problem, not allowed to have points of the form n log volume L0, like L0 equal to m below the green line. So in both cases, we have a contradiction. Unless x intersect equals x1, which means that the dimension, the rank of L1 intersect L2 equals the rank of L1, which means L1 intersect L2 equals L1, which means that L1 is contained in L2. And that's what we're trying to prove. We're trying to prove this nesting. So we've proved nesting. Also, all these subspaces are nested.
Yeah. Why did you have to invoke the intersection? If I go to the picture above, we now deduce that x plus and y plus lie on the line. Can we not directly from there deduce that?
X plus and y plus, x plus and y plus cannot even lie on the line if they are really strictly to the left or to the right of these points. Because if there was a point, say here, and a point, say here, then these points would not be extreme points anymore. They'd be convex combinations of these 2 points. And so the only case that's allowed is for this point to actually coincide with this point, and for this point to actually coincide with this point. So that means that the
right, okay. Okay.
That means
there's also no proper x plus. Okay.
Yeah, that means we get this inclusion. Let's just do the proof of C. So let me remind you what C is. I'm not going to do the whole proof. What was C? Sorry, this is 1, 2. We've proved 1 and 2. Let's talk about 3. So 3 is saying something about for every intermediate subspace which appears in the filtration, the filtration restricted to the initial part of the filtration up to and including that point is the filtration of that substance. That's what this statement is saying. So let's prove that. I think, yeah, these are, I called these A, B, and C, but I wanted to call these 1, 2, and 3. So that was 1. This is 2. Sorry for the mess. Now what happened? 2. 3. So the we had a set A, and let me just call that A of L, and A of L was the set that I had before. It's the set of points K co-volume, log co-volume. This is the set of points that we used to construct the filtration. So if we take an Li and look at, so let's just say that A, Li, is obviously contained in AL, right? For any Li contained in L, right? Because we're just taking some of the, when we take the definition of this set, we're only taking those sublattices that lie inside Li. So if they lie inside Li, they obviously lie inside L. So this set is clearly a subset of this set. So that means that A plus Li lies above in the notation that we had before. These are the sets that we're taking the convex hull of. However, the points in the profile of L with rank 0 less than or equal to Li also belong to this set by part 2. Part 2 said that that we have nesting, and so if I look at, where did this go? The definition of the filtration. If I look at the logs of the co-volumes of the elements that appear here, well, they do belong, they're part of the filtration of L, but they belong to Li. They're just part of Li by step 2. We have nesting. And so since we have nesting, they belong to both sets. So the sets have to coincide. Profile of Li is the profile of L restricted to X coordinate in this range. Okay, and so that proves the first statement in 3, and the second statement of 3 and 4 are exercises. I'll let you think about them. So this was the proof of this result about the filtration. And now I'm going to move to another topic. So this filtration is something that I've been really excited about for years, and this is kind of on a personal note. I'm trying to get more and more people interested in this filtration. It's not usually studied in by people studying geometry of numbers. It comes, as I said, from algebraic geometry. And like I said, in recent years, there have been quite a few results that have been obtained using this filtration, because it really does better than the Minkowski successive minima. So I hope we'll see examples of that later on in the course. Okay, so what's our next goal? Our next goal is to construct a space of lattices. So the space I want to think about all lattices in a fixed dimension n as being points of a space, and I want to give this space more structure. So today we'll be discussing the topology of this space, or we're going to put a metric on this space, and we're going to consider it as a metric space. And in the future, we're also going to put measures on this space, so we're going to have to put, sigma algebras and measures on this space of all possible lattices. So let's recall what the collection of all these lattices is as a set. So in the first lecture I showed that there's a bijection between all lattices in Rn and the quotient GL in R over GL in Z. So let me remind you how this goes. This is n by n invertible real matrices. This is n by n integer matrices with determinant plus minus 1. And so this right-hand side are the cosets, the right cosets for this subgroup acting on this space. And the mapping that establishes this bijection is the following. You take a coset here, and you map it to the image of Zn, the standard lattice Zn, under this element of GLNR. And again, you should note that this is a coset, but the mapping is defined in terms of a representative. If you change representatives, you're changing by multiplying by an element of this group in here, but this group stabilizes Zn, as we saw. So this is a well-defined mapping, and the reason it's a bijection is maybe color, because we saw it. This is a bijection because GL and R acts transitively on all lattices, and GL and Z is the stabilizer of the standard lattice Zn. And for the same reason, you can make a similar bijection between all lattices.
Sorry.
Yeah.
Is it not SL and Z? I mean GL and Z and Z.
So, GL and Z, the notation in this field is slightly confusing. So GL and Z, by definition, consists only of integers matrices with determinant plus minus 1. It's not, you might think this is integer matrices with non-zero determinant, but somehow just the definition of this group means it's those matrices which have non-zero, the integer matrices with non-zero determinant whose inverse also is made of integer matrices. So that forces the determinant to be plus or minus 1. And we check that this is exactly the stabilizer of Zn in this action. And the second bijection is all lattices of covolume 1. And that's in bijection with SL and R over SL and Z. And here this is n by n real matrices of determinant 1, and this is n by n integer matrices of determinant 1. And the proof of this bijection is exactly the same. It's the same mapping again. I mean, you just have to check. Let me also do this in brown. Check that SL and R is transitive on lattices of volume 1, and S on Z is stabilizer of Zn. So this gives us a certain preferred parameterization of the space of lattices. The collection of, right now it's a collection. The collection of all lattices of covolume 1 is parameterized in this way. The collection of all lattices of any covolume is parameterized by this quotient. And these structures can be used to put topologies and measures on the space of lattices. And that's why I'm mentioning them again. And that's what we're going to do now. So the topology can be introduced in several different ways, which turn out to be equivalent. And I'm going to use the metric on a bigger space, which is the space of closed subsets of R to the n. So CL R to the n is the collection of all closed subsets of R to the n. Okay, this is some huge collection of sets. It includes Rn. All of Rn is a closed subset, so it's a point. It includes the empty set. It includes Z to the n because it's a lattice, and a lattice is a closed set. It includes lots and lots and lots and lots of points inside. And there's a metric on this space. So obviously, so the lattices in Rn, it's just obviously just a subset of this big set because lattices are closed sets. And I'm going to put a metric on this set, and this metric will induce a metric on this set just by restricting. So what's the metric? The metric is called the Chaboty-Fell metric. So on closed of Rn, define the Chaboty-Fell metric by the following formula. D, capital D for the distance. I'm going to use capital D for the distance for this Chaboty-Fell metric. The distance between two closed sets is the infimum of the following set. 1, union epsilons in 0, 1 with the following property. For all x in the ball around the origin of radius 1 over epsilon intersect x, there exists y in y with distance from x to y less than epsilon, and also for symmetrically, I'm going to flip in the roles of x and y. Okay, so let's try to parse this definition. So first of all, I put a 1 here. I'm taking an inf. I put a 1 here. The reason I put in a 1 here is that this set in principle might be an empty set, and the only reasonable way to take the inf of an empty set is to declare the empty set has infinity, and that would be fine, except metrics are usually supposed to take values which are real, positive, real numbers. And so I'm just putting this 1 in to truncate the function. It's not, this is not the important piece. What matters here, the distance between two sets is always bounded above by 1, and what we care about is when is the distance small. So let's say the distance is small if there are small epsilons which satisfy this property. Suppose epsilon is, say, 1 over 100, then this number is 100. So what we're looking at x, only the points in the ball of radius 100 around the origin, and we want for each point of x in that ball for there to be a nearby point of y, where nearby is epsilon. This norm here is the L2 norm on this space. And then we do the symmetric thing with the roles of x and y reversed. And if you're used to the Hausdorff metric on non-empty compact subsets of a compact metric space, this is almost the same definition, except we don't take the distance, the Hausdorff metric for the entire distance between x and 1, we only are interested in the intersection of x with a large ball. So the topology says the two sets are close if there's a very large ball on which they look very close to each other. They appear to be very, very close to each other. That's the definition of the metric. So exercise is to check that this is really a metric. In other words, it satisfies the axioms of metrics. And that's exercise number 1. Exercise number 2 is with this metric, the collection of all closed subsets of Rn becomes a compact space. It's a compact metric space. So I'm going to now state a theorem, and we'll prove it after the break. And the theorem gives us a way of understanding how, if we take this metric and restrict it to lattices, what does it mean for a sequence of lattices to converge to another lattice with respect to this metric? So that'll be let's call that a proposition. So let's let L, L1, L2, etc. be lattices in Rn. The following are equivalent. The sequence of lattices Lj converges to this lattice L with respect to this Chaboty-Fell metric. You notice that n, the letter n is fixed. It's the dimension of this space. And so j is my index for this sequence. And so as j goes to infinity, these lattices are converging to this lattice with respect to the Chaboty-Fell topology or the Chaboty-Fell metric. That's the first condition. The second condition is made of 2 parts, so star, for all, let's call it 1, say. For every element of L, there exists a sequence of elements of Lj such that the Lj's converge to L with j goes to infinity. And 2, if Jk is a subsequence and Ljk is an element of Ljk such that the lim k goes to infinity of these Ljk exists, then this lim is in L. So in other words, what is this telling you? It's telling you that this lattice, the elements of this lattice, can be detected by the elements of these lattices when we have convergence by taking subsequences of elements that converge. So every point in the lattice, the limit lattice, is a limit of points from the pre-limit lattices, and every limit of points from the primitive lattices, even if you pass through subsequences, has to belong to the limiting lattice. That's B. C, for any basis, V1 up to Vn of L, there exists bases V1j, Vnj of Lj, such that for I equals 1 to n, the Vj i's converge as j goes to infinity to Vi. Okay, so you can detect the convergence by having a sequence of bases in the lattices that converge. Fourth item in the list involves matrices. So writing Lj equals Gzn, Gjzn, Gj in Gl and R, and L equals G of Zn, G of Zn, G on R, there exist gamma J's in G and Z such that Gj gamma J converges as J goes to infinity to G. So in terms of coset representatives, you identify the lattice L with the coset of an element G, and this just means that you can choose coset representatives for this lattice. Maybe they're given by this coset representative, but maybe you have to choose a different coset representative. So with this new representative, we have convergence of the matrices. This is convergence. Here we see convergence in GLNR. GLNR, the collection of matrices, is naturally, you can think of it as being a subspace of n by n matrices, and therefore there's a notion of convergence in GLNR. Okay, so those are the four different characterizations of this metric. All those four statements are equivalent. Let me add one more thing to the statement. The functions that send L to lambda 1 of L, the shortest vector, L to the covolume of L, are both continuous with respect to B, i.e. Lj tends to L implies lambda 1 L of 0 tends to lambda 1 of L, covolume Lj tends to covolume. Okay, so let's take a break, and after the break, I'll prove the statement. Any questions about the statement before we go for a break? All right, so 10-minute break, and then I'll prove this proposition. Okay, let me continue. So I'm reminding you what the statement of the proposition is. We have 4 necessary and sufficient conditions for the convergence in terms of this Chabot-Fell metric, and we also have the continuity of the co-volume function and of the lambda1 function. So in the chat, Manuel asked about the functions alpha I, whether they're continuous. They are continuous. You can also ask about the lambda j's for higher j. They're also continuous, and that's part of your exercise sheet. The updated exercise sheet is on the course webpage, okay? Now, the logic of the proof will be that I'll prove A implies B implies C implies D implies A, but along the way, I'll also prove that these continuity statements. Particularly, this one will be sort of important for the proof, so I'll prove it after I've as some kind of intermediate step during the proof. All right, so let's prove that A implies B. So what is A? A is the convergence of Lj to the convergence of the lattice Lj to the lattice L in terms of this D, which is this Chabot-Fell metric. So we're just assuming this. And what do we want to prove? We want to prove 2 statements. One is that every element of the limit lattice is a limit of elements of the prelimit lattices. And we want to show that if you have any convergent subsequence of things in the prelimit lattices, you have to converge to something in the limit lattice. So those are the 2 statements. So let's let epsilon j be 2 times this distance. So that's number also going to 0. So this means that these epsilon j's here satisfy the condition that appears here in the definition of the Chabot-Fell metric. So every point in one set is close up to epsilon to a point in the other set, as long as that point is in a ball of radius at most 1 over epsilon. So I want to prove 2 statements, 1 and 2. Statement 1, I'm given an element in L. I choose J0 so that 1 over epsilon J is bigger than the norm of L for all J bigger than J0. Then by the definition, of epsilon j, L is close up to epsilon j to Lj, so that means that there exists an element Lj in the set Lj such that the distance from L to Lj is less than epsilon j. And this goes to 0, so Lj goes to L, and so we've satisfied 1. Part 2. Suppose Ljk is a sequence of elements from a subsequence of the Ljks. Ljk converges to L, and I want to show that L is contained in this little element in L. So let J is bigger than, let's call this guy L infinity, bigger than L infinity norm plus 1 for all J bigger than J0. And the distance from Lj to L infinity is less than 1 for all J bigger than J0. So if I choose J0 in this way, and again I apply the definition of the metric of the Chabot-Fell norm metric D with one of these sets being LJK and the other one being L, I get then by definition of D, there exists some element, let's call them LJ bar in L, such that the distance from LJK bar in L, the distance from LJK bar to LJK is less than epsilon, which is going to 0. And so LJK bar tends to L infinity, and that means that L infinity is in L. So L is closed. L is closed, and we found a sequence of elements from L that converges to L infinity, so L infinity must be in L. So that proves the second statement in B. So now I want to prove that B implies C. Let's scroll back up to remind ourselves what C is. So this is B, what we just proved, and this is C. We can find for any basis of L, we can find elements of a basis of the LJs which tend to this basis. And before proving it, I'll prove the statement that I said I will make, which is the continuity of the lambda i's. So we first show that if you assume B, then you get that the lambda 1 of LJ tends to lambda 1 of L. Proof of this, let's first of all look at the lim sup of these numbers. And this is, so, oh, sorry, let me move this a little bit. So let's let Vj in Lj such that lambda 1 of Lj is the norm of Vj. So the Vj's are the shortest non-zero vectors in Lj. And so the lim sup of these LJs I'm sorry, that's not what I want. Sorry. Sorry. So by statement B, I can choose the vector V that realizes the first successive minimum on L, and I can find a sequence of Vj and Lj that tends to it. Okay, and so that's my definition of the Vj's. And then so the lim sup, so each one of these Vj's is some non-zero vector. So we have this inequality. So that means that we have that the lim sup of the lambda 1 of the LJs is less than or equal to lambda 1 of L. And now let C be the lim inf as j goes to infinity of these numbers. And suppose by contradiction, that C is strictly smaller than lambda 1 of L. I want to prove equality, so I want to prove that C equals lambda 1 of L. If it's strictly smaller, there are two cases. If C is some positive number, then that means that there exists a subsequence along which the lim inf is attained, and Vjk in Ljk such that the norm of VJK is lambda 1 of LJK. And these vectors, VJK, are non-zero vectors, and their length tends to a non-zero number. And so the passing to a further subsequence, I can assume that the VJKs converge to some vector V infinity. And this vector is in L, and this follows from part B. And so what that means is that C, which is the lim of the norms of the VJKs, is equal to the norm of V infinity, which is an upper bound for lambda 1 of L. So I got a contradiction. Because I assume that C was, so this and this are contradicting each other. If this number C is 0, then for large enough J, Lj, or large enough K, I meant, Ljk contains a vector Vjk of length less than lambda 1 of L divided by 3, multiplying by an integer, get a vector that's called Ujk in Ljk of length in lambda 1 of L over 3, 2 times lambda 1 over L over 3. Right? Because if I have a vector that's shorter than this number, and then I start multiplying it by 1, 2, 3, 4, etc., eventually it's going to fall inside this range, and these vectors are in this lattice. Now, passing to a further subsequence, Ujk converges some W in L. Norm of W is in this range. And we get a contradiction again in the same way. And so that proves the claim that I made that lambda 1 is continuous. And now let's go back to the proof that, so now we can continue with the proof that B implies C. Let's remind ourselves what C is again. Where is this? This is C. So the point that's not completely trivial, it follows from B immediately that for V1, we can find a sequence V1J that converges to V1. So similarly for V2 up to Vn, that's just exactly statement 1 of B. But it's not immediate that this sequence of vectors is actually a basis for Lj, and that's what we want to do now. We want to take care of. So by B, there exists a sequence, and notation is going to be a little bit nasty. So a sequence Vij, I'm going to put the parameter tending to infinity on top. That's always going to be J. So there's a Vij, and this is an element of Lj such that this happens. V1 up to Vn were our chosen lattice of L. And let's let Lj bar be the span over Z of Vj1 up to Vjn. So Lj bar is some subgroup of Lj, and it's clear that the conclusion that I want to reach is satisfied. So conclusion is satisfied for Lj bar instead of Lj. In other words, if I knew that Lj bar was equal to Lj for all large j, then I would have exactly what I want. So suppose by contradiction, that along an infinite subsequence of j's, Lj bar is not the same as Lj. And from now on, I'm going to pass the subsequences without giving them, without changing the notation for subsequence, because there are going to be several subsequences. So then, along this subsequence, we have that Lj, the index of Lj bar in Lj is 1. Now, we proved already by the continuity of lambda 1, we know that lambda 1 of Lj is bounded below by some number independent of j, because these are converging to lambda 1 of L. So let's write down an inequality. Let's say they're bounded. Yeah, so I'll write down the inequality and then I'll explain. So there exists a positive eta such that we have the following thing. Sorry. It's a positive eta and a positive c, such that we have this. I should have said, I'm sorry, I should have said conclusion is satisfied for Lj bar instead of Lj. And here I also should say that also the covolume of J bar, which is the absolute value of the determinant of a matrix that you get by putting these vectors as column vectors, the covolume has an expression in terms of the absolute value of the determinant. Determinant and absolute value are continuous operations, and so the covolume of Lj of Lj bar, I'm sorry, converges to the covolume of L. And so here I get these inequalities. Let's review the inequalities. So I've just told you that lambda 1 of Lj is bounded below by some number, so positive number. So lambda 1 of Lj to the power n is also bounded below by some number, and I'll call that number eta. And this is clearly less than or equal to this. By the Minkowski second theorem, we have this inequality. So this is Minkowski second theorem. And this inequality is clear because Lj bar is a sublattice of Lj. And I just explained to you that this is a convergent sequence. So all of these things put together imply that the covolume of Lj is in a bounded range. So passing to a further subsequence, we can ensure that the covolume of Lj converges to some positive number. Let's call that positive number m. And I'm sorry, I'm not going to call it m. M is coming later. Converges to some positive number, and the covolume of Lj bar, which is the index, we have this formula, and I want to call this number m, again along a subsequence. Okay, so these numbers converge, and therefore these numbers converge. These numbers are integers, positive integers not equal to 1, but by a contradictory assumption. So passing to a subsequence, I can just say that they have a fixed common value m. Okay, and now I'm going to use a statement that we proved in lecture 1 about sublattices. So by a result proved in lecture 1, there's a basis uj1 up to ujn of Lj such that v1j is a11 uj1, v2j is a21 uj1 plus a22 uj2, etc. Vnj is an1 uj1 plus etc. And the coefficients that appear here satisfy the following bounds. So the AKL here, all of these coefficients depend on J. So I'm not writing this because it would just be too much notations, but I'll just mention it. So all the AKLs depend on J, and they satisfy the following bounds. These are all integers. The diagonal terms, A, I, are all natural numbers, so they're all positive. The product is the index of the subgroup Lj bar inside Lj, so that's this number m that I wrote down before. And the off-diagonal terms are bounded in terms of the diagonal terms in every row. So these are bounds we saw in lecture 1. So passing to a further subsequence, since everything here is now bounded, I can assume that all the AKL are independent of J. All right, so in my notation, I wrote down these coefficients, these integer coefficients, and I didn't write down the dependence on J. But in principle, there is a dependence on J, but we have bounds on everything in sight. So these numbers are integers multiplying to a fixed number, so they're bounded. These numbers are bounded by the diagonal terms, so all these numbers are bounded. And so we have infinitely many sequences of these coefficients taking values in a bounded set. So we can pass to a subsequence where all of these are indeed constant. So now that they're constant, there's a first index where the diagonal term is not 1. So let I0 be the smallest index so that uj0 is not in Lj bar, i.e. a11 equals dot 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 equals up to I0, not including I0, these coefficients are all 1, and then these diagonal coefficients are all 1, and then at I0, the coefficient is not 1. Why am I saying that? If you look at this diagonal base change here, if this guy is 1, then these two guys are the same. If this guy is 1 and this guy is also 1, then this guy is in the span of these guys over Z. What you're seeing in this form is that the VIs are in the Z span of the UIs. But as long as the diagonal terms are 1, you can invert this system of equations and get the UIs as combinations of the VIs, again, over Z, as long as these numbers are 1. If these numbers are not 1, then that's no longer the case. And let's write a little m for this number. So this is an integer bigger than 1. And so the let's look at uji0 and express it. Yeah, I'll just write things. I'll write the bottom line and then I'll explain it again. So for I going from 1 to I0 minus 1, ui is in the Z span of V1 up to VI. That's what I said before. And I0 is in 1 over n, or has the form, sorry, can be written as okay. So again, the first thing that I said here is just saying that up until I0 minus 1, I can invert this triangular system of equations and write the UIs as elements as in the Z span of the VIs. Now what happens at the location UI0? Suppose that I0 is 2. So we can look at this formula here. So this number is no longer 1. Let's move the UIs over to the other side and divide through by this number. Then we see that this formula, this expression is this expression minus a integer linear combination of VIs with smaller index divided by A22, which is an integer n. So that gives us this form here.
Sorry, you don't have an index j anymore.
Everywhere there should be an index j, right?
Right. Okay, you're not making a statement about L.
Yeah, I'm trying to, yeah, so there could be j's sort of everywhere here. Everything actually depends on j. Okay, but the point is that the coefficient here is not 1. There is at least one, sorry, it's not an integer. There's at least one coefficient which is not an integer. And that means that uji0 is not in LJ, right? Because we've expressed it as a the basis of sorry, it's not in LJ bar. The basis of LJ bar are these VIs, and we've expressed Uij0 as a linear combination of the Vij's, but the coefficients are not integer, and there's a unique way to, because this is the basis of the entire space, there's a unique way to write this vector as a linear combination of these vectors. So if this number here is not an integer, that means that this vector is not an element of LJ bar. Okay, now I can pass to a subsequence. And I get that Ui0j converges to some U, and U is in L by B. And U has the form, the same form. So it's sum I going from 1 to I0, Bi Vj I, Bi0 I0 equals 1 over n, which is not in Z. So this contradicts, oops, there shouldn't be a J here. Passing to a limit, the V, all of these vectors converge to the corresponding vectors V1 up to Vn, and the coefficients are all bounded. So passing to subsequences, I get this type of formula for U, and U belongs to L. That was what V guaranteed, but we just wrote it down as a linear combination of VI's with one of the coefficients non-zero. This is a contradiction to the assumption that VI's are basis. Okay, so that implies C. And let's now prove that C implies D. Let's go back to the top and remind ourselves what C is and what D is. Yeah. So this is what we just proved, that you can, for every basis of L, you can choose corresponding bases of LJ. And now we want to express this in terms of matrices. That's easy enough. So we can write the LJs as GJ Zn, L as GZn. We can also write LJ as VJ1, VJn. This is the matrix whose columns are these VI's multiplied by Zn. Once you have a lattice for the ZJs, you know that you can do that. And let's call this matrix, say, HJ. So this is HJZn. So that means that there exists, since HJ and GJ are both representing the same lattice using different bases, there's an element of GL and Z. So it exists, let's call it tau J in GL and Z, such that GJ tau J equals HJ. Now HJ converges to V1 up to Vn. Let's call this guy H. HZn is L. And so H is G tau for some tau in GL and Z. So now if I multiply by tau inverse and tau J inverse, so I get that GJ, let's see. So if gamma J is tau J tau inverse, then GJ gamma J equals GJ tau J tau inverse and I get what I wanted. So this was statement D. Last statement, I want to go back from this choice of coset representatives in GLNR over GLNZ to the Chaboty-Feld matrix. And so for that, I'll use the operator norm on matrices. So denote for G and GLNR, the operator norm of G okay? And given an epsilon, let's let J0 be large enough so that for all J, at least J0, we have two things, Gj gamma J, G inverse minus the identity in operator norm is less than epsilon squared, and same thing with the inverse of this map. So G gamma J inverse, Gj inverse. Okay, so the we have from D that Gj gamma J tends to G, and so multiplying by the inverse and looking at the operator norm, all of these operations are continuous with respect to the operator norm. We see that we can ensure that this holds. And similarly, we can ensure that this holds. So this holds for all large enough J. And what are these mappings? The mapping Gj gamma J G inverse maps L, which is Gzn, to Lj, which is Gj Zn. So it's a linear transformation, and that's what it does to all elements. And similarly, the opposite, the inverse of this map, this should be a Gj, I'm sorry. Maps Lj to L. So now let's take X in L in the ball of radius 1 over epsilon, and then Gj gamma J G inverse X is an element of Lj, and the distance between them, oops. Sorry, computer wants to stop. Okay, the distance between these guys is less than epsilon, right? So this quantity here is bounded above by the norm of X times the operator norm of this matrix minus identity, which is less than epsilon squared. And so I get this, and similarly, for X in Lj intersect this ball. I get that G gamma J inverse Gj inverse X minus X is less than epsilon. So putting these two together and using the definition of D, I get this. Okay, I think this should be a, okay. So that proves the theorem. So I proved the chain of equivalences, and along the way, I used B to prove the continuity of the lambda 1 function. I also showed the continuity of the covolume function when I was proving, I think it was B or maybe C, and I get the claim. Let me give some remarks about this theorem. So remarks. The first remark is that the equivalence between A and B works for any sequence in this Chaboty space, in the space of closed subsets. So going up to the statement of the theorem, you see that I have a necessary sufficient condition for convergence with respect to this Chaboty distance. And so it's geometrical, and we've proved it only for lattices. Along the way, we used lambda 1 and so on. Where did this go? And I'm claiming that you don't need to, it works for every sequence of sets in this Chaboty space. I'm sorry. It's taking me a long time to scroll up. Here we go. Right. So the equivalence of convergence with respect to the Chaboty metric and this notion of having an approximation of one set by another in terms of sequences, that's completely general, even though we didn't prove it in complete generality, but I'm remarking that it's completely general. And you can, and it'll be on the exercise sheet, so you can convince yourself of that. And oops, so this is an exercise. And the second comment is the topology induced by this metric D is the quotient topology. GR over GR. So I'm not assuming too much background in terms of topology. Maybe some of you have not taken the course in topology, but for those of you who have taken a course on topology, you know that whenever you have a topological space and an equivalence relation on it, you can form something called the quotient topology. So this is the smallest topology on this quotient. Making the projection map continuous. So in the topology course, it's usually given by some kind of abstract characterizations. And here we have the quotient topology in very concrete terms. So if you, I'll let you sort of convince yourself, for those of you who know a little bit of topology, I'll let you convince yourself that this is true. Okay, so what have we done? We've given the space of lattices the structure of a topological space with this particular metric. And next week, we're going to use this in order to, we're going to be able to use some topological considerations in order to get some non-trivial information about lattices. So that's coming next week. Okay, see you all next week.
Bye-bye, thank you.
Bye.
Bye-bye.
Bye.
Thanks.
Thank you.
Thank you.